Today we're integrating. Okay guys, so today we'd like to evaluate an integral from 0 to 100 of the floor of x multiplied by the ceiling of x, and that's actually a problem from 2023 MIT integration bee. So first of all, what the hell's going on in this problem? You see, this function right over here, denoted by something on L, and then x, then an inverted L on the right hand side closing it, let's say, is the so-called floor function. The floor function takes some number and brings it down to the closest integer value that is less than that number. And so we see that if we had, let's say, 3.14, which is an approximation of pi, then the floor function would bring it to 3. If we had, let's say, 2.78, then the floor function would bring it to 2. It's not rounding it up and or down, it's just kind of bringing it down to the closest integer value that is less than the given number. And well, if we take a floor of just an integer, let's say of 2, well, that's just gonna give us 2. Yeah, something like this. And then we have this second weird function, which is this guy right over here, like an inverted floor. And this actually is kind of like an inverted floor. It works pretty similarly, but not quite. So this is the so-called ceiling function. The ceiling function takes a number, let's once again take the approximation of pi, and it spits out the closest integer value that is greater than or equal to the given number. So for the case of 4.14, it will give us 4. For 2.5, it will give us 3, and so on and so forth. For, let's say, 5, which is an integer already, it will just spit out 5 itself, no problem. And so how the hell are we supposed to integrate it? I mean, well, those functions are not quite continuous as you might expect. They have like those weird bumps where they are just constant on the interval between some integer and another integer, and they just kind of hop to the next integer value once they change the interval from a plus 1 to a plus 1, a plus 2. And so how are we supposed to integrate those? Well, I would actually like to use a pretty neat trick here. So as I already said, those functions on the interval, let's say from a to a plus 1, will behave something like this. So the the floor of x on this interval will be equal to a. However, the ceiling of x on this interval will be equal to a plus 1. And we can make good use of this fact right over here. So let me maybe move it right here, so we remember it here. So from a to a plus 1. And so we can just go on and kind of rewrite this integral from 0 to 100 of the floor of x times the ceiling of x dx as just a sum of a bunch of integrals. So let's say from n equal to 0 to 99 of the integral from n to n plus 1 of the floor of x times the ceiling of x dx. And so what did I do here? Well, nothing really. I just kind of split this integral right over here into 100 smaller integrals. It doesn't really change anything. It doesn't change the final result because some integrals, they can be split up due to addition. We can just add integrals and subtract integrals from one another. There is no problem in that. Okay, but the nice thing is that right now we change the interval on which we define those integrals to the interval from n to n plus 1. And why is that awesome? Because the floor and ceiling functions are gonna have pretty constant values on those in those intervals. And so we can rewrite this entire thing once again as the sum from n equal to 0 to 99 from the integral from n to n plus 1. The floor of x is gonna quite nicely change into just n, then we multiply by x, and then we check what's going to happen to the ceiling of x. Well, that's going to be always n plus 1 on the interval between n and n plus 1. So apart from those two endpoints, but they're, just so abysmal that we don't really have to care about them. They're, infinitely small. And so we multiply it by n plus 1 right over here, and we do all of it with respect to x. However, the nice thing is that, well, n and n plus 1 are just constants with respect to x, and we are only integrating this guy with respect to x. So we can just go on and take those out of the integral. Lovely, let's do it. So what we're going to be left with after doing so is the sum from n equal to 0 to 99, from n of n multiplied by n plus 1 and multiplied by the integral, oh, that's a poor looking integral, from n to n plus 1 of x dx. Lovely. Well, now what we could do is, well, evaluate this integral, each one of those integrals, and just kind of get an expression in terms of n plus 1 and n, do something and manipulate it here instead of the sum, but honestly, it's gonna get kind of messy. So, we're gonna get, some n's in the fourth power, in the third power. It's not gonna be really elegant. So what I would like to do here is change those bounds of integration. I would like to make those bounds no longer, well, be in terms of n, so that when I evaluate those integrals at last, it's gonna look a little bit better. So how do I want to change those bounds of integration? I would like to do a needle trick. I would like to apply a change of variables. So I would like to apply the change of variables. I would like to say that my x is going to be equal to some t plus n. Well, my dx is not going to is not going to change. It's going to be equal to dt, so I won't have to multiply the integrand by anything. That's a nice thing. However, my bounds are going to change quite significantly. So that's going to be a separation line, and now I would like to calculate the bounds. So when x is equal to n, t will be equal to 0, because t plus n is supposed to be equal to n. However, when x is equal to n plus 1, t will be equal to 1, because t plus n is supposed to be equal to n plus 1. And so I can rewrite my integral from from n to n plus 1 of x dx as the integral from 0 to 1 of t plus n dt. And now we can just go on and plug this guy here into my original problem. And so let's go on and do it. Oh,
That may be beyond my abilities at the moment.
Fortunately, it's not beyond my abilities. So let's do it. Siri is not good at math. Apparently. Okay, so it's gonna be the sum from n equal to 0 up to 99 of n multiplied by n plus 1 times that beautiful integral from 0 to 1 of t plus n dt. Lovely, but what is the integral from 0 to 1 of t plus n dt? Well, this guy right here is just going to be equal to the integral of between 0 and 1 of t and the integral of between 0 and 1 of n. So it's going to be 1/2 plus the integral between 0 and 1 of n is just going to be, well, n. Lovely. And so it's going to be equal to double n plus 1 all over 2. Perfect. So we can just go on and plug this guy here, getting it is going to be equal to the sum from n equal to 0 up to 99 of n plus 1 multiplied by double n plus 1, everything by 2. That's the expression. Okay, and this actually looks, this expression here looks kind of like the sum of consecutive squares, but if I were to now change this entire sum into sum from n equal to 0 to 99, and then sum from m equal to 1 to n of m squared, that would get like messy as hell. So let's maybe try and not do that. Let's try and change the stuff here inside of the sum, so that maybe we could, separate it and get a bunch of sums instead of one sum of, well, product of things. Let's try and do it. So, well, this thing right there, 2n plus 1, actually is equal to n plus 1 plus n. I mean, yeah, surprise, surprise, yeah? But what is special about this kind of form this expression actually can take? Well, here we've got an n plus 1, and here we've got an n. So maybe it would be beneficial to try and, multiply it with respect to this form and not this particular form. Let's try and do it. So that would be, that would all turn out to be a sum from n equal to 0 to 99 of, and now, well, n times n plus 1 times n. That's gonna be n squared multiplied by n plus 1 all over 2, and then plus n multiplied by n plus 1 squared all over 2. Perfect. And well, now it really looks it looks like something that is, well, possible to deal with, because look, this guy right here, this n squared times n plus 1, that's going to be just equal to n cubed plus n squared. We know how to calculate the sum of consecutive cubes. Is just, I think it was the square of the sum of consecutive numbers in the first power, and we know the formula for the sum of consecutive squares. I mean, at least we should know it from high school. If you don't know it, then I will just show it to you. I'm not going to be proving it because I think I proved it in one of my videos on induction or something like this. It's a nice exercise to practice induction. And so the only problem is that this guy right over there, n times n plus 1 squared, there is, well, it's just going to be messy. Like, it will get quite messy, honestly. But the nice thing is that we can actually separate those sums to become two, let's say, separate sums, yeah? And then just change the bounds on which we sum stuff up for this expression, this n times n plus 1 all squared. Okay, let's try and do it then. So what are we going to get after something like this? We're gonna get the sum from, from n equal to 0 to 99, or maybe a half of that sum of n cubed plus n squared. This is exactly what we are getting from this sum right here. And now the second one, because the second one is going to be more interesting. That's going to be a half of that sum from n equal to 0 to 99 of n multiplied by n plus 1 squared. However, I would like to change it in such a way that I could get here something like, maybe n minus 1 times n squared. I mean, can I do it? Can I shift those indexes here in the sigma subscript and the upscript such that I could do this? Such that I could get this kind of a situation? Well, I can do it. I just have to switch n so that it's beginning to count from 1 and that it stops to count at 100. That will no problem, because then I just have to shift the index here to n minus 1 multiplied by n squared. So let's do it. And when we do it, we will get, well, on the left hand side of the plus sign, we're just gonna get this sum once again, and I'm too lazy to write it down again, so I'll just copy it. And here on the right hand side of the plus sign, what we're gonna get is a half of the sum from n being equal to 1 to 100 of n minus 1 times n squared. Lovely, because this is just the sum of n cubed minus n squared. Oh, I forgot to put parentheses here. Yeah, something like this. That's absolutely awesome, because now we can just go on and, well, separate those sums. I mean, make all of those kind of make all those n's have their own sigma sign. There is no problem in doing that. So we're gonna get a half of the sum of n equal to 0, from n equal to 0 to n equal to 99 of n cubed, plus a half of that sum from n equal to 0 to 99 from n squared, then plus a half of that sum from n equal to 1 to 100 from n cubed, and then minus, so negative 1/2 of that sum from n equal to 1 to 100 of n squared. And we know how to calculate each one of those, because this sum of first consecutive of n consecutive squares, something like this, is actually equal to n multiplied by n plus 1 multiplied by double n plus 1 all over 6. Yeah, and also the sum of all first consecutive cube, first n consecutive cubes is equal to n times n plus 1 all over 2 everything squared. Yeah? Oh, I had to crack my neck. Okay, so now that we know those two formulas, let's say I will color them, I know orange is a nice color. I will resize those and put them right here. And now let's rewrite our sums in terms of that stuff. So what we're gonna get is, from the first sum is gonna be a half of the sum of from n equal to 0 to 99 of n cubed. That's gonna be a half 100 multiplied, oh my god, I'm not good with technology, all over 2 and squared. Then what we're gonna get, so that was the first sum right over here. Now we are going for the second sum. That's gonna be a half of, well, 100 multiplied by 101 and multiplied by 201, everything divided by 6, everything divided by 6. Awesome. And now this was the pink guy. Now let's go on and mark this one as the blue guy. That will be 1/2 of the sum of the n consecutive cubes. That was 99 and 100. Now it's better. Here 100 times 101 all over 2 squared, and then minus 1/2 of that sum of 100 times 101 times 201. Yeah, I now see that I also made a mistake in the second guy. So just a second, I will correct it there. That's the orange person, and this is... I'm not trying to be racist or anything, please no. Here I'm getting 99 times 100. Oh my god, 99 times 2 is 189 plus 1. Am I right? Oh, no, I'm not right. It's 198. It's gonna be 199, I suppose. Yeah, because it's 200 minus 1 plus 1 makes minus 2 plus 1. That makes sense, yeah. So, well, now this all just numerical stuff that I'm not gonna be counting because I'm too lazy for that. But this is something numerical. And so this is actually the final result. And we don't have to go any further now. You can just go on and kind of calculate it. And so what we did here is, well, we kind of noticed that the floor function on the interval between a and a plus 1 is equal to a, that the ceiling function on the interval between a and a plus 1 is equal to a plus 1. We applied that stuff after splitting our original integral into 100 smaller integrals, splitting the interval into 100 smaller intervals within n and n plus 1. Then we just took out those floor and ceiling functions, which turned out, as said earlier, to be equal to, well, the bottom and the upper bound of the range. No, yeah, I forgot. Okay, the range itself. Inevol itself, thank you. And that was that was a nice trick, definitely. Then what we did is we wanted to just kind of get rid of those ends in those lower and upper bound of that integrand right over here. So what we did is we changed variables. After changing variables, we got that that really cute. I will do it in pink, so it's even more cute. So right here we got that integral from 0 to 1 of t plus n dt, which was pretty easy to calculate. What we did then is we just kind of split up the sum we got into two sums. In one of those we changed the indexes from n equal to 0 to 99 to n equal to 1 to 100, so we could change the sum we're summing over a little bit. And then after just splitting those sums up finally and applying some high school formulas for the sums of cubes and squares, we got the final numerical result and finished our problem. So I hope you guys enjoyed it, and see you in the next one. Bye.